All right, good afternoon, guys. What I'm going to talk about today is pulling apart a business domain through analysis and applying SOA principles, domain-driven design concepts, and a lot of the messaging patterns found in the Enterprise Integration Pattern book. My name is Gary Stonerock II. I'm the lead systems architect at Almac Clinical Technologies. We recently finished a rebuild of their clinical trial management platform, and I'm going to be discussing some of the challenges we faced and how we overcame them. I'm going to start with an overview of the domain and a particular problem we were trying to solve. I'll then take a small part of that problem to decompose some of its requirements so we can evaluate the various design decisions and the trade-offs associated with them. Then I'll take a step back to describe the overall solutions in terms of SOA services. And finally, we'll wrap up with a brief summary of how it turned out. So a few disclaimers before we get started. One, I obviously can't give out the exact solutions as they are owned by my employer. Two, some of the concepts and solutions have been simplified a little bit anyway, as it would require too much knowledge into the domain to make sense. But three, I do have to give a sufficient background into the domain for my examples to make sense. So starting off with some basic terminology. A study or clinical trial is a controlled process to explore if a drug is effective and safe for humans. Typical treatments are an active treatment, which would be the drug, or a placebo treatment, which would be something that would look exactly like the drug. Patients would then be randomized to receive one of these treatments, and the purpose of that is so no one knows which treatment they're actually getting. Patients participate in the study at a site. A site could be a doctor's office or a hospital. And when they come in to receive a treatment at one of these sites, they receive it in the form of a kit. An example of a kit could be this blister pack where each one of these pills is either the active treatment or the placebo treatment. IXRS 3.0 is Almac's next generation clinical trial management platform that we built. And its capabilities are divided into two main areas, patient management and supply management. I'm going to focus more on the supply management side of things, more specifically its forecasting capability. So getting into a little bit more terminology on that side. When I say supply, I could be referring to the thing in inventory or the act of providing the thing in inventory. The supplies we're managing are the kits that we're giving out to the patients, and how we're managing that is similar to the vendor-managed inventory model where the supplier is managing the customer's supplies on their behalf. There's two main conflicting goals that we have to deal with. The first is we want to minimize the waste. Drugs tend to be fairly expensive with very short expiration dates, so if a site has too many supplies, we'll end up throwing a lot of them away. But we also want to prevent a shortage. So we have to ensure if patients are coming into the site that there's actually enough supplies for them to give them a full treatment. Balancing these goals can be quite tricky, and we do that through the use of supply strategies. These strategies is what drives and powers our forecasting process. So getting into the actual process, when we started, we had an existing platform to contend with. Our requirements were phrased in terms of the older solutions, and a lot of the concepts and language were more technical oriented than domain oriented. Does that sound familiar to everybody? It was implemented as a batch job, which iterated through many entities and large transactions and was very synchronous in nature. It was implemented using thousands of lines of T-SQL because it required so much data in the database to do what it needed to do. How many people have heard that it has to be done in the database because it requires too much data? Yeah. So getting into the actual process, it's broken down into three main areas: determining the supply strategy to use, calculating the various levels, then comparing those levels to calculate the demand. The first area we're going to get into is determining the supply strategy. This is the area we're going to get into pretty fine-grained requirements, so please bear with me as I step through them. The other areas will be more high-level from an SOA service perspective. To start a forecast, the system will first need to find a valid supply strategy and determine what supply phase the site is in. Taking this high-level requirement and breaking into two parts, the first part, the system will find a valid supply strategy by, then the second part, the system will determine what supply phase the site is in. So taking just the first part and expanding on this requirement, the system will find a valid supply strategy by first checking if the site has a supply strategy that is active. If not, the system will check if the site's country has a default supply strategy that is active. If none exists, stop processing and send an alert to the administrator. So before picking this guy apart, I want to take a step back and look at the general pattern this requirement fits. If some condition, use this value, else if some other condition, use this other value, and if we can't figure it out, well then just throw an error. So if we were going to take a look at the conditions, what we would notice is these are made up into two distinctive parts. The first part, if the site has A, and if the site's country has A. These are relationship existence checks. The second part, that is active, these are status checks. Who's received requirements like these before? So these are fairly standard requirements. If we were to take a step back and implement and create a model, a typical implementation might look something like this. We could have a supply strategy with an isActive flag. We could have a relationship from a site to a supply strategy. We could have a relationship from a country to a supply strategy to represent that default value. Then finally, we could have a relationship from a site to a country to represent the country the site is actually in. If we were going to take this model and write some queries against it to implement those requirements, we might end up with something like this. And this was really our first iteration and our first pass at it. The first query is going to the site to see if it has a supply strategy, joining on, well, let's see if that works, joining on the supply strategy to ensure we're only getting an active one. If that returns a result, cool. If not, we perform another query, joining from the site to the country, again, joining on supply strategy to ensure we're only getting an active one. If we find one, cool. If not, we return null. Who's written code like this before? Yeah, so if you write code for a living and your hand's not up, you're lying. This is pretty standard queries here. So this is similar to where we started, and for us to get some better options, we do have to do some more analysis. So let's start with the status and try to break this guy down. What exactly does it mean to be active or inactive? What we learned was it was really about being approved or not approved for use. But why do we need approval? As it turns out, approval is a fairly common idea in this domain for a lot of different reasons. I'll give two of them. One, we might be addressing regulatory concerns. Or two, we might be trying to mitigate the risk of someone doing something that'll result in a negative business consequence. Would we ever stop using an approved one? We might, if it turned out to be an ineffective way of managing supplies, or if something happened in the trial where we radically wanted to change how we're managing supplies. How often these activities happen? Turns out not that frequent, because more often than not, we're making minor adjustments to supply strategies to better align with reality and what's actually happening in the study. So quite infrequent, actually. Do we really need to evaluate this logic in real time all the time, every time we're running a forecast? How can we better encapsulate this? What was funny was the answer was right in front of our face, for use. Why should we be able to use a supply strategy if it's not currently approved to be used? So what we did was we were able to isolate and shift that logic out of the problem and enforce those relationship rules when establishing the relationship. So if a site wanted to use a supply strategy, it should have to choose from a list of currently approved supply strategies. If we no longer wanted to use a supply strategy and wanted to deactivate it, we should have to replace all its current usages with another currently approved supply strategy. So now going back, before I move on, by mixing responsibilities, what we end up doing is we end up creating a whole lot of accidental complexity, where separating these responsibilities, we create two simple solutions. Going back to the requirement here, now we can remove this from the problem altogether, and our overall solution becomes simpler. Before moving to the next part of the condition, I first want to address the concept of a failure. So these types of requirements also create a lot of complexity. If none exist, stop processing and send an alert. The challenge here is we often get caught up in fine-grained details of requirements or implementation details that we don't take a step back to look at the process as a whole. What we should be asking ourselves is, how can we create a design such that the process always logically succeeds? This is rather simple. We just don't start, enable, or activate the process until we have all the required data in the system. But a lot of times when we try to do something like that, it ends up being a cluster of complexity written as queries, just grabbing data from all over the system. So what we could do is we could use the aggregate pattern from DDD to explicitly model this. We could create an aggregate to encapsulate the enabling and activating of the process. We could add a property to it for each thing that must logically happen first as a prerequisite. We could subscribe to events to ensure that we're aware of when these things actually happen and it's decoupled from the actual thing happening. We could prevent that state transition until we have everything that we need. Then finally, once we have that data, we could prevent it from being deleted, so the invariants are always enforced. If we were to, this could actually be implemented as a saga. We chose not to, and the reason for that is if a user was going to enable or activate something, we could give them a list of things that are missing that they need to do and even walk them through getting that data into the system. So if we were to take this type of aggregate and put it in front of the forecasting process, we actually could eliminate this from the requirements as well, and that's what we did. What we're left with is a fairly straightforward requirement now. The system will find a supply strategy by first checking if the site has a supply strategy. If not, the system will use the site's country's default supply strategy. So we're using one or the other. So the requirement's simplified. Let's take a look at what it's done to our basic model here. It only eliminated the need for this guy. Everything else we still actually need. But our queries, it did simplify them quite a bit. We no longer need to do the join on the supply strategy to get the status. And now, because the process will always logically succeed, we're guaranteed that default value to be there, so we can remove all that other code. So while this is simplified, we actually did a lot better than that, but it required just a little bit more analysis. Why would we be changing the country's default supply strategy and how often? Well, I more or less already answered this a little bit earlier, but sometimes when we're doing analysis, we need to hear things multiple times or a few different ways for it to actually sink in. More often than not, we're making minor adjustments to supply strategies rather than changing them altogether. So it's not that frequent of activity. Have we used factors other than the country to determine this in the past, and do we envision this might change in the future? The answers to these questions in this case were yes and yes, but these types of questions are great to figure out the volatility of a particular detail so we know what level of flexibility or what levels of abstraction we need to incorporate in the software. So let's take all this and explore a couple different options. If we started with the site supply strategy, this would exist if a site wanted to use a particular supply strategy. If it didn't exist, that's when we would need the country information to do all the other joins. But is there a design that we could think of where we would only need this aggregate to figure it out? If we were able to denormalize and replicate the country's default supply strategy into it, we could actually achieve that. When starting a forecast, we could just load this up for that particular site. If the supply strategy ID is null, then we would use the default value. What we've learned through our analysis is this data is slowly changing and consistency isn't a very large concern. But I don't want to stop there. I want to take that country detail and encapsulate it behind some other abstraction so that could change in isolation in the future. Then finally, I want to remove and defer the naming of this aggregate until our analysis is complete. More often than not, when we defer the naming of something, we end up with a much more cohesive thing and a much more clear and concise name. So how can we encapsulate that? Not only do we need something to represent this abstraction, but we also need a mechanism for replicating these changes down to these aggregates we're trying to create. A Saga is perfect for this. So here, if we have a Saga subscribing to the country's default supply strategy being accepted, correlating off the country, we could take that supply strategy and replicate it down to these other aggregates. It'd be cool if we could do this, but the first problem that we have to deal with is if this Saga aggregate is on the country level and these other aggregates are on the site level, how do we know which sites to update? We could subscribe to another event, the SiteActivated event, which would have the site ID and the country ID. If we did that, we could build up a list of sites in that country within this Saga. We would then know what sites to send these updates for. The next problem we're faced with is, do we need to know when all these updates have been completed? And it's important when we're building systems like this that we're designing in eventual consistency and not introducing inconsistencies. So in this case, we do need to do that. But before I get into the solution that we went with, I first want to take a step back to talk about Sagas in general. Sagas are an implementation of a process manager where messages come into it and messages go out of it. It's also an aggregate, so it shouldn't be reaching into another aggregate to know it should or should not do something. If it needs to be aware of something or do some work, that needs to be encapsulated behind a message. So if our Saga needs to be aware of all these updates being completed, it needs to be told that. A good pattern for this is the request-reply pattern, which works well when you're communicating in a style of like a conversation. So I tell you to do something, then you reply back with a response. So one option we could go with is we could reply back per update. The problem with this approach is as the number of sites in the country increase, the more reply messages increase, the more contention we'll have on that single Saga when they're receiving these messages. A better approach might be to wait some period of time to check for completion. So this decouples the actual completion checking from the amount of data that is in the Saga, so it scales a whole lot better. So taking this approach and applying it to our Saga here, when we're sending all these update commands, we actually could set a timeout for ourselves. And then when we time out, we could send a command to count the number of completed updates. Once a handler would receive this, it would then check to see if we're done and could reply back with the number of completed updates. When the number of completed updates equals the number of sites in this Saga, then we now know all the updates have been completed. So we were able to create a design where we only needed this aggregate to figure out what supply strategy to use, and we were able to do that by applying analysis and pulling the problem apart. I still want to defer the naming of this because we're going to come back to them. So like I mentioned, that was only the first half. The second half of this, expanding on this requirement, the system will determine what supply phase the site is in based on the following factors. If the site has had an order that hasn't been canceled, then the site is in the resupply phase. If not, the site is in the initial phase. The first part I want to take is an order that hasn't been canceled. What exactly does it mean to cancel an order in this particular domain? This might seem like a pretty simple requirement, and it might seem like a user would actually be able to cancel an order. In our case, once an order is submitted into our system, it's broken into multiple shipments. Then at that point, its entire life cycle is managed on the shipment level and not the order level. So a user would be canceling a shipment and not an order. Initially, we found this quite confusing when we were doing our analysis because they used the terminology order and shipment interchangeably. So how do we implement this requirement if you can't cancel an order? Well, again, this turns out to be a fairly straightforward saga. We could have a saga subscribing to the shipments being accepted for that order, maintaining a list of its current shipments. If one of those shipments was canceled, we could remove it from the list of shipments, and if the list of shipments ever became empty, we would then know all the shipments in the order have been canceled, therefore the order's canceled. If we wanted to be able to mark this saga as complete, we would have to know it's impossible to cancel this order, and the only way for us to know that is if one of the shipments actually arrived at the site. We would know that during our shipment acknowledgement process, so we could subscribe to a shipment being acknowledged and then be able to mark this guy as complete. So that was that part of the requirement. Taking the rest of it, if the site has had an order that hasn't been canceled, then the site is in the resupply phase, else we're in the initial phase. So what this really means is we start in the initial phase. Once the site has one or more orders, we transition into the resupply phase. But if that condition changes, we have to be rolled back to the initial phase. So the properties of this problem is my state changes are driven by side effects from other processes. Again, a Saga is perfect for modeling something like this. So if a site was activated, we could create a Saga for that site, managing its current supply phase, transitioning it into the initial phase. Once an order would be accepted for that site, we could then start building up a list of orders for that site and transition it into the resupply phase. If one of the orders was canceled, we could then remove it from that list, and if the list ever became empty, we could then return it back to the previous phase. Looking at this aggregate that we've been trying to build up over time here, the only stuff we have in here currently is enough information to determine the supply strategy to use for the forecast. But like I mentioned, that was only really half of the problem. The other half was, what is the current supply phase we're in? So we could actually subscribe to these events and record what the current supply phase is, and then we would know everything in this aggregate to start a forecast. If we wanted to name this aggregate, we would have to take a step back and look at the data that's in it and what would be the most appropriate name. In our case, forecasting strategy. And the behavior of this aggregate is to start a forecast. So all that other logic in those requirements we were able to pull out, and we optimized the data for exactly how it was used. And we were able to do this through pulling apart the problem and doing analysis. So that was determining a supply strategy, and that was more fine-grained requirement stuff. Moving to calculating the levels, this is going to be more high-level SOA type stuff. So the complexity here is calculating these various levels requires so much data to actually calculate that what we'd like to be able to do is take each one of these calculations in isolation and aggregate them as we go. A perfect pattern for this is the scatter-gather pattern from the Enterprise Integration Pattern Book. So if we were to take a look at some services, here the forecasting service and n number of services that want to participate in these calculations, here service A, B, and C. The scatter portion of it is the forecasting service publishing out to the world an external event that we're currently forecasting the demand for a particular site. The two pieces of information on there would be the forecast ID, so we would be able to correlate all the calculations and results to that particular forecast. Then the second is the supply strategy ID, so we know what values to plug into these equations. Now, as far as the supply strategy is concerned, that's actually partitioned across all the different services. Each service would actually define the supply strategy in terms of its capability. So it would have intimate knowledge of the data structures and concepts used within a particular service. It's important to note here that there is no single supply strategy, that it's partitioned across many different services where each service only owns a subset of its data, and the only data shared across services is its ID. The gather portion of this is after the services finish doing what they need to do from a calculation perspective, replying back to the forecasting service, and the forecasting service aggregating all these results. The data on these messages would be a canonical data model we call kit type quantities, which is a list of kit type IDs and the quantities associated with each one. If we were to take a look inside the forecasting service during this gather portion, what we would find is multiple aggregators, one per level that we're trying to calculate, implemented as a saga. So this saga would be listening for these different things being calculated, correlating against that forecast ID, building up the results as we go, then finally calculating that particular level. If we were to look inside of one of the services actually collaborating and doing some calculations, what we would find is a processing pipeline. So the forecasting demand event would come in here. The first component we would have in this pipeline would be a message filter. The purpose of this is if a service no longer wanted to participate in the forecasting process for a particular site, we could short circuit and just reply back with a null result, meaning an empty list of kit type quantities. An example where we did this is if a site no longer wanted to enroll and randomize patients into the study, that we wouldn't have to be predictive in that area anymore. We could just reply back with an empty list of kit type quantities. The next component in this pipeline is a splitter. This is where a splitter takes one piece of work and breaks it up into n number pieces of work. We are able to use these a lot when we found natural partitions in the problem that we could process things in parallel. Next was the content enricher that would look up values from the supply strategy to enrich the messages being fed into the calculator. Then once we did the calculation, we would then be aggregating the results to ultimately reply back with a list of kit type quantities. A few things I want to mention about this design. We were effectively able to separate our reads from our writes. This entire processing pipeline is optimized for calculating and not writing to the database. So we did have to capture a lot of data along the way for historical purposes. So what we did was we captured all this data and put it on internal events, published them out so we could write to the database in separate transactions. Now I want to clarify, when I say internal and external events, I'm purely talking from a logical service perspective and not a physical systems one. I think sometimes people confuse the two. With internal events, it's not really about the amount of data that we're putting on them, it's the type of data. That the data on internal events will most likely represent internal concepts to a service, but once we're crossing a service boundary, we want to be sure to only be sharing stable business concepts. Now, why do we care so much about that? With SOA, it's really about encapsulating variability and volatility behind stable business concepts in the domain. So when the business changes, not everything in the world is changing. The change is isolated to a particular service. What we've seen so far is multiple services communicating and collaborating during the forecasting process, but there might be other activities going on throughout the system over time that might influence what some of the services do during the forecasting process. So what we'd like to be able to do is share this information so we can better encapsulate all the logic to reside in one single service. All the data needed for a service to fulfill its business capability should be inside of it. So a service should never be reaching into another service to know it should or should not do something. And I want to reiterate that this information that we're sharing would only be stable business abstractions. Let me give an example of that. So something I mentioned a few times today, the SiteActivated event, I want to illustrate why this is a stable business concept. So what exactly is a site? A site is a place for patients to participate in the study. Is that likely ever to change? They have to participate in the study somewhere. And sites are also a place for regulatory processes to occur. That's also highly unlikely to change. What is the activation of the site? Well, leading up to the activation, there's a lot of external processes that are going on from a regulatory perspective, and the activation of it signifies that the site is now able and ready to have patients there participating in the study. So both of these are fairly stable, common ideas in the domain. What about the data on them? So site ID, why would we need that? Well, we need to know what site we're referring to, right? The country ID, this actually took me a fairly long time to get this. And that's because most of the domains I've worked in, it's been an implementation detail which country things are in. So as I was doing the analysis and pulling these requirements apart, everything seemed to want to know what country something was in. So it was very hard to envision there could be multiple services in the system without duplicating this data. So what I learned was that one of the things that drives a lot of the things in this domain are the regulatory concerns. What drives the regulations? The countries themselves. So it turns out that countries were not only a stable part of the domain, but they were central to it. What about the relationship from the site to the country? Could the site ever change a country? It's a physical place, right? So the data representing that relationship is immutable. So in summary, a stable business abstraction, in this case, we have stable and immutable data being shared during a well-known, well-defined activity. So that's calculating the various levels. Getting into the last part, I'm only going to skim over this guy because it's pretty straightforward. Basically, we're comparing those levels using some basic logic and then determining if the site does or does not need supplies. But what I do want to get into is the other processes that trigger the forecasting process. One of them is the automated ordering process. So here we would have a Saga waiting for a scheduled forecast to be completed. Once it is, if the forecast deemed there was a need for supplies at the site, we would submit an order on behalf of the site. And this is how we ensure sites in an automated fashion have enough supplies for their patients. Another is the supplier forecasting report. One of the details I've glossed over a little bit is most of these activities come from a supplier's point of view. So we never have just one forecast going on at one particular time. We actually have forecasts going on for every single site the supplier actually supplies. So if we were going to generate this report, we would have to wait for all those forecasts to be completed. I'm going to give a little bit simpler solution than using a Saga here. If your only requirement is detecting completion, you could actually just use a handler to do that. A handler could receive a check message to go to the database and see if things are done. If not, it could defer another check message to itself and keep on going until it actually detects completion. When it does, it could then publish out that it's completed. So this is a real lightweight mechanism. If you don't have any other requirements, you don't need something as heavy as a Saga. To wrap up, I want to summarize some of the benefits we were able to achieve applying this to these types of techniques to the entire process and as well as the entire platform. The whole thing became a lot easier to reason about, that we didn't have to understand the whole thing at the same exact time to understand what to do. And we were able to conversate in higher levels of abstraction. Each part of the process became isolated with its single responsibility. So if we were going to change something, say the randomization strategy for a site or a study, we wouldn't have to do an impact analysis on the entire forecasting process. It would only be impacted in one particular spot. Our processes became a whole lot more reliable because we logically designed for them to succeed combined with the properties of reliability from messaging, everything became eventually consistent and eventually successful because we designed for them. There was a dramatic increase in performance. So like I mentioned, from a supplier's point of view, we're doing all these forecasts. This could take hours. Now it takes a minute or two. These were some pretty significant benefits, and I want to leave a couple closing thoughts on some lessons that we learned during this rebuild process from an analysis standpoint. The shortest path to solving the problem is analysis. That how do we know what to build if we don't understand the problem to begin with? We end up building a lot of accidental complexity into our solutions. Don't build software to requirements. Instead, use them to guide and support your analysis. Ask questions to yourself. So how can I better isolate this thing? How can I better encapsulate this thing? How can I not write this conditional statement? Optimize aggregates for the behavior they expose. So don't focus so much on the CRUD aspects of things or how data gets somewhere. Focus on the behavior the data affects. Model aggregate creation, state transitions, and relationships explicitly. Defer the naming of things. Encapsulate behind abstractions and communicate only through stable ones. So while you could apply this to many different things, the one that I want to emphasize the most is that of a service. So once we're crossing a service boundary, or if you're more familiar with domain-driven design, a bounded context boundary, we want to be sure to only expose data that represents stable business concepts. Patterns can provide guidance when exploring solutions. So patterns aren't meant to be the solution, but can be quite useful when shaping a solution or communicating it with others. If you were interested in this style of SOA or these types of analysis techniques, I'm going to be blogging about a lot of this stuff. I just started the blog, so please bear with me as I get it going. I'll also be here for the remaining of the conference, so if you want to talk to me about this stuff, if you want to give me feedback, I'll be here. So thank you, guys.